The current scientific understanding of time travel is rooted in theoretical physics, particularly within the framework of Einstein's theory of general relativity and quantum mechanics. While there are intriguing possibilities and theoretical concepts, it's important to note that practical time travel remains purely speculative at this point. According to the current understanding, 1. Time dilation. Time dilation is a well-established phenomenon in which time passes differently for objects moving at different speeds or experiencing different gravitational forces. This has been experimentally observed and verified. For example, astronauts who spend extended periods on the International Space Station age slightly slower than people on Earth due to the station's higher velocity and weaker gravitational field. 2. Wormholes. The concept of wormholes, also known as Einstein-Rosen bridges, emerges from Einstein's theory of general relativity. These hypothetical shortcuts in spacetime could potentially connect two distant points, enabling travel through both space and time. However, substantial challenges, such as the need for exotic matter with negative energy density, currently make the practical realization of wormholes highly speculative. 3. Grandfather paradox and causality. Time travel theories often involve paradoxes, such as the grandfather paradox, in which a person travels back in time and does something that prevents their own existence. These paradoxes raise questions about the consistency of cause and effect. Resolving such paradoxes requires understanding the nature of causality and the possible existence of multiple timelines or self-consistent loops. 4. Quantum mechanics and time. Quantum mechanics introduces fascinating possibilities for time travel, such as closed time-like curves. These are hypothetical paths in spacetime that allow for time travel within the framework of quantum theory. However, the existence and practical utilization of closed time-like curves remain highly speculative and have not been observed in reality. 5. Energy requirements and technological limitations. The energy requirements for creating and manipulating the space-time fabric for time travel are currently beyond our technological capabilities. Additionally, the understanding and control of fundamental forces at extremely high energies, such as those found near black holes or in the early universe, are necessary for exploring the potential avenues of time travel. There are several key theories and frameworks that both support and challenge the possibility of time travel. Here are a few of them. 1. Einstein's theory of general relativity. Einstein's theory provides the foundation for our understanding of gravity and spacetime. It allows for the possibility of time travel through the concept of wormholes, which are hypothetical shortcuts in spacetime. However, the practical realization of wormholes requires the existence of exotic matter with negative energy density, which has not been observed and poses significant challenges. 2. Closed time-like curves. Closed time-like curves are paths in spacetime that, if traversed, would allow for time travel. They are allowed within the framework of certain mathematical solutions to Einstein's equations of general relativity, such as the Gödel metric and the Alcubierre drive. However, the existence of CTCs raises causality paradoxes and challenges our understanding of the flow of time. 3. Quantum mechanics. Quantum mechanics introduces intriguing possibilities for time travel. Quantum phenomena, such as quantum entanglement and quantum teleportation, have been explored as potential mechanisms for transmitting information backward in time. However, the interpretation and application of quantum mechanics to time travel are still subjects of ongoing research and debate. 4. Novikov's self-consistency principle. This principle, proposed by physicist Igor Novikov, suggests that the laws of physics inherently prevent the occurrence of paradoxes in the presence of time travel. It suggests that any actions taken by a time traveler in the past would be self-consistent and would ultimately result in the preservation of the existing timeline, avoiding paradoxes like the grandfather paradox. However, this principle is not universally accepted, and alternative theories and interpretations exist. 5. Hawking's chronology protection conjecture, proposed by physicist Stephen Hawking. This conjecture suggests that the laws of physics prevent the formation of time loops or the occurrence of time travel on a macroscopic scale. scale. He proposes that the fundamental physical laws would conspire to avoid situations that lead to inconsistencies and paradoxes. While this conjecture provides a potential safeguard against time travel, its validity is still a subject of investigation. Time dilation is a phenomenon in which time passes differently for objects moving at different speeds or experiencing different gravitational forces. It is a consequence of Einstein's theory of relativity. Time dilation is important in the context of time travel because it suggests that if one could travel at extremely high speeds or near massive objects, they could experience time passing differently compared to others. This could potentially allow for scenarios where someone traveling at high speeds could experience less time passing relative to someone who remains stationary, effectively traveling into the future. However, practical time travel to the past or the creation of closed time-like curves still requires scientific breakthroughs beyond our current understanding. There are real-world examples and phenomena that resemble aspects of time travel or provide indirect evidence for its potential existence. 1. Gravitational time dilation. Near massive objects like black holes, the intense gravitational field can cause significant time dilation. This has been observed and confirmed through experiments and astronomical observations. It suggests that time can pass at different rates depending on the strength of gravity, opening up the possibility of time travel under extreme gravitational conditions. 2. Experimental verification of time dilation. High-precision experiments using atomic clocks have confirmed the effects of time dilation. For instance, scientists have observed that atomic clocks aboard GPS satellites, which experience weaker gravity and higher speeds relative to clocks on Earth, run slightly faster. This practical demonstration of time dilation supports the theoretical basis for time travel. 3. Theory of wormholes. The concept of wormholes, hypothetical shortcuts in space-time, has been proposed within the framework of general relativity. While their existence has not been confirmed, the mathematical equations allow for the theoretical possibility of traversable wormholes, which could potentially serve as portals for time travel. However, significant technological and scientific challenges must be overcome to harness such phenomena if they indeed exist. It's important to note that while these examples demonstrate intriguing aspects related to time dilation and the theoretical frameworks of wormholes, practical time travel and the creation of usable time machines are still purely speculative and require further scientific advancements.